So, hi. Congratulations, you made through this very last talk of the whole workshop. Okay, bear with me for another 60 minutes, then we're done. Okay, so I'll be talking about some work we do for scalable deep learning. And if you think about, I'm owner of a restaurant, I'm actually the guy who bring you dishes. Like we provide service to users like you guys. So, okay, so what is TAC? Who are we? Who we are? So we are a computing center in University of Texas. We are located in Austin, Texas, and we host several, like, from medium-sized to large-sized supercomputers, clusters for various types of computing needs, right? And we have users all over the country. And in particular, for machine learning and deep learning applications, this is a short list of our portfolio we're supporting. And I think this list is actually something I'm working on. Yeah. And first things first, like we're going to have NSF's largest supercomputer. I think by the end of the summer, it's coming soon. So before you lose interest to my talk, here's the most important thing. Like we're having a supercomputer. Bring your applications to our supercomputer. Okay, so it's a combined system. Like for the primary computer system is Intel-based, Intel Scalable processors for next generation. I'm not sure if I can talk about the particular code name, but it's Intel-based. And we have two GPU systems, one for double precision. We have 448 NVIDIA V100 GPUs. And for the single precision part, we have 456 Quadro RTX 5000 GPUs. Yeah. And interconnects the Mellanox, fetch rate topology, which is not fancy. We have storage, everything POSIX. And if you have and we have test beds ready for experiments with survey data. Yeah, we'll try to answer bigger questions with bigger data on bigger computers faster. So if you get your data ready, you want to explore deep learning methods for a particular problem, bring it to TAC. Okay, cool. So I say we are ready, and this is the actual work why I say it's ready. So I'll present some research we do over the past few years. The first one is scalable training algorithm. The second part is scalable and efficient I/O on supercomputers. The first part is about speeding up training with massive amount of processors without losing model performance. Like you want to scale out, but if you lose test performance, that's meaningless, right? So we did some work on this. And for the second part is like, when we first start supporting deep learning workloads, the I/O actually brings us some problem. Our system admins complains about like the slowdown or the performance of our system slows down and sometimes just unresponsive. So we designed some software system to tackle that issue. Okay, cool. First thing. So before we jump into that thing, I will first go over a little bit about data parallel training with synchronous SGD. So this is the intranode. This is the intranode parallelism case. Like you have GPU, a single CPU with multiple GPUs. What actually happens when you train on multiple devices? The things like you have variables, consider this as a model, and you replicate to different GPUs, and then you run the feed-forward process for deep learning and the computer loss. Then you can use this loss, compute the gradients with regard to each parameters in this model. And then the gradients are averaged on the host memory, and then the gradients are the averaged gradients are used to update the model. So this is how it works. And if you think about internode parallelism, the things like you don't compute average directly, but on each of the so we run an R-reduce operation if you know MPI. So basically, it's just gathering all the gradients from every single node and compute a sum stored somewhere, either in host memory or device memory, depending on the implementations. And the thing is, like we compute a sum of all the gradients. Then we do an average, then do the update. So it's quite similar. Yeah, it's just a sum stage. Okay, so the algorithm we look into is this layer-wise adaptive learning rate scaling. So one of Jimmy Demo students designed this algorithm when he was an intern at NVIDIA. So we collaborated with Jimmy's group on the thing. So the intuition is like learning rate should be adjusted according to the norm of the weights in each layer. So concretely, these are just tricks compared to the math. I mean, this is just tricks. And so these omegas are the weights in each individual layer, and we use fixed we use fixed scaling factor weight decays to update the weights in each layer individually. So we verify the effectiveness of the thing and combine it with other techniques such as linear scaling. Like linear scaling is like when you double the batch size, you also double the learning rate, because if given an example of fixed epoch, basically you visit the data set for a fixed number of times, double the batch size, meaning you are going to apply for the gradient updates a half of the frequencies. And we also combine the warm-up for the first several epochs. We scale the learning rate from small to the target rate, and then gradually to avoid the trap in a non-optimal area. Okay, so this shows the effectiveness of the algorithm. So the red line is the baseline case with batch size of 256, and we increase this batch size to 32K for the ImageNet data set, and this is what we have without any instrument. And after applying this large algorithm, we were able to preserve this test accuracy for ImageNet training with Resonance 50. And this is showing the effectiveness. And mapping it to a supercomputer, this is what we have. So this whole thing is implemented with Intel Caffe, and we scaled on like from 256 to 3,000, over 3,000 Intel Xeon Phi processors. Like this gold line is the ideal scaling curve, and the blue bars are actually our measurements. So you see from the 1,000 KL nodes, the efficiency actually starts to drop, and over 3,000 KNLs, the efficiency is only about over 50%. So the reason is like the R-reduced implementation is a schedule-reduced algorithm which scales linearly to the number of nodes. So after a certain scale, the communication overhead dominates. So that's why the efficiency keeps drops. Okay, so, and we were able to finish this 90 epoch Resonance 50 training with about 20 minutes. And we were the fastest record in the whole world for 2 weeks. And then we were passed by a company called Preferred Networks. They were using, I can't remember exactly, maybe 1,500 GPUs. And there are some follow-up work who all use this large algorithm, but with but they treat the precision for the computation part. So from what we did, like they finished, group of scientists from Hong Kong and Tencent in China, they finished this training in 6.6 minutes, then 224 seconds with 2,000 V100 GPUs from Sony, and 2.2 minutes with 1K Google TPU v3 TPU pod. Yeah. So this is the first work. And the second thing is about the I/O. So if you look at the applications we are supporting, and these are just examples, and the image classification data set, if we're using the ImageNet data set, it has about 1.3 million files, 2002 directories, total size of 140 gigabytes, which is okay. The individual file size is about 100 kilobytes. And we have another application comes from the neuroscience research, like they were trying to train a super resolution model to raise the resolution of electron microscopy images. Okay, so they have about 0.6 million images spread in 6 directories, about 500 gigabytes. And the third application is from, they have a new name. They used to call ISIS, which is not a good name. It's called Institute for Computational and Engineering. I'm sorry, I can't remember. Yeah, so they were actually to predict the plasma reactor disruption, and it was called Fusion. The network is called Fusion Recursive Neural Network. They have about 0.6 million small files in one directory, and the total size about 1.7 terabytes. Okay, so the problem. So deep learning is long-lasting, repeated, high volume, and highly concurrent file access can easily saturate the metadata service and data service of a traditional file system. So if you put it on Lustre and you access data from there, it's going to be problematic. So Resonance 50 with Keras, TensorFlow, and Harvard on 16 nodes, each with 4 GPUs, will incur 128K static and redirection operations with 64-way concurrent access, 117 million operations on the metadata, and over 180 million read operations with the same concurrency. So if you're a system administrator of supercomputers, you won't be happy about this, right? Cool. So, and they ran for 8 hours. Cool. So this is what actually looks like if you host the data from Elaster and you scale the training from 1 node to 16 nodes, each with 4 GPUs, like the efficiency is only about 30%, okay? Cool, so what we do is to design and build a system called FanStore. We leverage local storage and interconnect to reduce the I/O traffic between compute nodes and the share file system. Basically, you load it to the local disk, and we provide, so we place the metadata and file data across nodes to enable high-performance read and write. And we preserve a POSIX compliant interface for users' convenience. So we did this in a very, very, very uncommon ways, like we preserve the POSIX interface by intercepting your function call for data access and replace the several first instructions to call our library. So for users, if you are working with POSIX format data, POSIX compatible data, you don't have to change your application. So you view FanStore as a share file system. Yeah, and we enhance the data storage capacity of existing hardware with compression. Okay, supports, and we implement specifically, since it's instruction set specific, we support it on x86 and Power 9 architectures. Cool. So this is what it looks like from a architecture point of view. So data is partitioned here. We partition the data set into large partitions, and each of the node loads one partition, from my point of view. And the metadata is replicated in RAM, so every node has a copy of all the metadata. And file access functions are intercepted and handled in user space. Remote file access is in the form of MPI round-trip message. And if the data is stored local, then you access file locally. Yeah. So that's it. And mapping it to Res 50 training cases, like we can achieve about over 90% of efficiency on 16 nodes with 64 GPUs. And what does this implicate for, with FanStore? So we don't have to change data access method in TensorFlow PyTorch program or Keras program. If you can validate your program at small scale on the share file system, you don't have to change your program. Just change the data path, and you can work. It will scale. We can achieve 70 to 100% read performance compared to the raw hardware because of this function interception POSIX compliant interface. And we increase the processing capability of existing storage hardware with compression. Well, I didn't talk about it with much detail, but we can do it. And we are able to enable efficient and scalable I/O for distributed training with millions of small files. And what it implies to this community is if you have applications that has a lot of files, like FIS file, FIS data, or and other formats, it's not a problem. Bring it to us. We will get it ready to you. Okay, so that's my talk. Awesome.